Good day, everyone. My name is Abraham Abe, and I'm a PhD student. At the University of Calabria in Life Science and Technology at the Department of Chemistry and Chemical Technologies. I work with the research group of Professor Cesare Oliviero Rossi. He spoke earlier, and I would like to give a presentation on a food-based bioadditive for improving the mechanical and rheological properties of bitumen binder in road pavements. This is a part of the molecular structure of the food-based bioadditive that we'll be using, and it will be incorporated into bitumen binder in the road pavements to improve the quality, the rheological properties of the bitumen binder in the road pavements. So the aim or the scope of this study is to investigate, identify, and characterize the antioxidant effect of the food-based chemical additive, which we gave the name CRH, on bitumen to slow down aging of the asphalt. Because we know that oxidation of the asphalt pavement is a big problem, and this causes different problems like rotting of the asphalt pavement and the different types of aging. These are the different types of aging that we can experience with the asphalt pavement: the little type, the well-balanced, and the highly associated aging process. And all of these are dependent on the temperature. So the temperature resistance of the asphalt pavement is very important on the lifespan of the asphalt pavement. In general, as colleagues, you all know what the warm mix asphalt is. The warm mix asphalt, of course, it's a technology that is used to produce asphalt at temperatures around 100, 110 degrees, slightly above that. And it was developed, of course, to reduce the pollution effects, the emission of greenhouse gases, and to help asphalt workers to reduce the risk. Now, the technique we use to try to improve the bitumen binder is the addition of additive to improve the bitumen's properties. Now, we used two types of bitumen in this study. The first bitumen is called the LC50 bitumen, and it has a penetration grade of 50-70. And it was supplied to us by Loprete Costruzioni Stradali, which is a company that we collaborate with here. This is called and the penetration grade is 170 to 210, which means it is softer. This bitumen is softer than this bitumen. Now, we also used the additive, the food-based additive that we used. We used one type of additive, but it has different analogs, different types of the same additive. The first one is CRH, as I said, CRHD, which is a variant. It is an analog of CRH additive and CRM additive. They literally have the same molecular structure. They are just variants. They are isomers of the same compound. Now, I will speak a little bit about the additive. They're food-based chemicals of the heptanoid family, and they have symmetric molecules. This is an illustration of a similar compound, because I cannot speak a lot about these additives because of copyright reasons. The company that supplied us the additive, because of the copyright reason, I cannot speak so much about the characteristics and the properties. But the additive is a natural phenol. This is another characteristic of the CRH additive. It is derived naturally from, it's a phenol. in general. Now, the exact nature of the CRH additive is not known because researchers are still trying to characterize the bioavailability of this additive. The bioavailability in the sense that the bioavailability of a substance is the amount of a substance that is readily usable, the amount of a substance that can be used in a system in general. So CRH additive has some antioxidant effect, and we try to characterize this in this study. Now, how we prepared our samples, it's quite easy to prepare the samples. You add the CRH additive, which is in the form of a powder, to the bitumen, and you add it into a container with a high-speed shear mixer at the RPM between 500 and 700 at a temperature of 140 to 160 degrees, and you leave under agitation for 60 minutes. After the preparation of the sample, you take some sample droplets, which is this, some sample droplets of the sample, and you take it to rheological analysis. Now, we used two different types of techniques in this study. The first technique is the dynamic shear rheology, which I think we all know what it is. And the second technique is the atomic force microscopy. Now, the rheological analysis. The principle of shear rheometry is very straightforward. Rheometry is when the material of interest is subjected to a shear, which in a way that the mechanical response is measured. This rheometer measures the mechanical response of the sample that you apply as shear in form of a similar to stress, okay? And we measure the mechanical response of that. After the rheological analysis of the samples, we arrived at some results. Here, the pure bitumen, this is the LC50, which is the hard bitumen, the one that with the penetration grade of 50 and 70. Here, the red profile here is for the pure bitumen, which has a transition point, a temperature transition, because in general, we measure the transition point of the substance of the bitumen sample by temperature. So the sample which has a red profile, which is the reference sample, the pure bitumen, is the red one, and it has a transition point at about 60 degrees, all right, as we can see here. Now, the blue profile, which is this, is the bitumen with 1% of the bioadditive. And we can see here that the transition point is about 66 degrees, which means there is a difference of about 6 degrees between here and here, which means the bioadditive made it more strong, make the conglomerate more strong. And this increases the temperature resistance of the road pavement that will be made with this bitumen with the additive. As we can see for some of the other analogs, the variants of the same additive, we can see here with the pink profile here, the pink profile gave us the best result, which is about 76 degrees. 76 degrees compared to 60 degrees here. That's about 16 degrees of a difference between the modified sample and the pristine bitumen pure sample. So this increases the temperature resistance of the bitumen sample. So it will increase the temperature resistance of the road pavement made by this bitumen with the additive. As we can see also the yellow profile, which is also the bitumen with another variant of the same additive. Here you can see that it's about 66 or 67 degrees, which is also an improvement of the rheological property of the bitumen. Now, this is another result, rheological result of another bitumen sample, which is the soft bitumen, the one that has a penetration point, the penetration grade of 170 to 210. This, you can see that because of the nature of that bitumen, because it is softer, the pure bitumen has a transition point around 51 degrees centigrade, which of course means that the bitumen is softer. And you can see here with the blue profile is something here, something similar around here. You can see that the transition is around 61 to 62 degrees. 61 degrees and 50 degrees, that is about 10 or 11 degrees Celsius of difference, which means it improves, it increases the temperature resistance of the bitumen sample, which means it will increase the temperature resistance of any road pavement that is made with this additivated bitumen. We can see that we have similar profile for the blue, the pink, and the yellow samples, which are all modified samples, the samples that are modified with the bioadditive. These results in general mean that the bioadditive has some antioxidant effect, which means it will reduce the oxidation with time, because oxidation is a big problem on the bitumen pavement, on the road pavement, the asphalt pavement, because with time it oxidizes and it reduces the strength of the aggregate, of the conglomerate. So these results show that, yeah, the bioadditive actually improves the rheological profile, the rheological characteristics of the bitumen. This is now, when we were preparing the bitumen, if you remember, I said here that we leave it under agitation for 60 minutes, that is an hour in the sample preparation. We also tried to see if we leave the preparation time for more than 1 hour. We tried 2 hours of agitation time, which we got these results here. We tried the agitation time of 2 hours, okay? The agitation time of 2 hours to see if maybe it can give any significant effect in the final sample. And you see that here, still the transition is around 51 degrees, but with the sample we prepared in 1 hour, it still remained at about 60 degrees, which is 10 degrees of difference. But after we left it for 2 hours, it increased a little bit more to about 62, 63 degrees, which means that maybe it increases the temperature resistance, or it increased the number of asphaltenes in the bitumen, which means it made it a little bit more hard. So we're trying to characterize if this is a very good effect or if this is a slight disadvantage. Now, we calculated the differences in the transition points of the samples, the pure sample and the modified sample. Now, the pure sample of LC50, which is the hard bitumen, the one with the 50-70 penetration grade, has a transition point, a transition temperature of 60 degrees. While the one with the additive, you see 66.5, it increased the transition point, which is a good thing. It improved the rheological characteristics. For another variant, we have 67.5 degrees, and here we have 68.5 degrees, which is a very, very good result. For the second bitumen, which is C170 with a penetration grade of 170 and 210, we had a transition temperature of 51 degrees. Then when we modified with the additive, we saw that we have 62 degrees. And here we have 60 degrees, and here we have 61 degrees, which shows that the additive also improved the rheological profile, the rheological characteristics of both bitumen samples. Now, we move to the atomic force microscopy analysis. We try to understand on a microstructural level to see if there were any changes in the microstructure of the bitumen. that was analyzed. So we got pictures similar to this. Sorry if I use this. This is not the real result. Now here are the results. But in general, atomic force microscopy, before I speak about the results, belongs to a family of scanning probe microscopes, which scans the microstructure of the bitumen. Now, the results that we obtained from the pristine bitumen of the C170, which is the soft bitumen, you can see here, this is a topographic image of the atomic force microscope, and this is a phase image. They are similar, it's just the pictures are the same. It's just that this is phase contrast and this is topographic. And with the with the topographic image that we can see, we see that the domains, these little domains here, they are the asphaltenes, they are the hard part of the bitumen, which confirms the colloidal model of bitumen. So here we have these domains of the asphaltenes, which have less than 4 micrometers in size, the domains. Okay, they have 4 micrometers in size, less than 4 micrometers in size. You see the domains here, they are small. The asphaltenes of the pure pristine bitumen. Now, when we added the bioadditive, you can see that the domains, these domains, they increased slightly in size. You can see here with the magnification that we used here, that these domain sizes are similar but a little bit bigger with this CRM. With the CRH, we even obtained bigger domains. You can see here, the domains were bigger than 4 micrometers. We have about domains of about 5 micrometers in size, which means that this bioadditive increased the rheological properties of the bitumen by increasing the domain size of the asphaltenes present in the bitumen, which means it makes the bitumen a little bit more resistant to temperature because of it increased the size of the asphaltenes and made them bigger in the colloidal system. As you can see here, the one with the CRHD, you can see that the domains are similar in size to this one, even though they're slightly bigger. The domains here were about 5.5 micrometers to about 6 micrometers in size. So we can see that this also improved the microstructural quality of the bitumen. Now, we analyzed the samples that we left for 2 hours. Remember, I told you that we also prepare some samples for 2 hours just to see if it will improve. When we checked under the atomic force microscope, the ones we used for 2 hours, the asphaltenes were not in optimal condition because the asphaltenes became very hard. The domains, they remain of normal size, but they became very large and hard. They agglomerated together, they fused together to form this agglomeration, which makes it hard and maybe makes it easier to break. So it means that 1 hour time of agitation is the optimum time for the preparation of samples. It's better to prepare your samples around 1 hour. It's better to not leave them to stay for about 2 hours because you ruin the domain structure on a microstructural level. So the LC50 bitumen, which is the stronger bitumen, the 50-70 penetration grade, we also analyzed that under the atomic force microscope. And these domains, you can see that it has more asphaltenes here. The domains are more. This is the hard part, and this dark part is the soft part, the oil, the maltines, and all of that. While these are the asphaltenes domains, you can see that it has a higher penetration grade, which is 50-70, which makes it stronger. And you can see that it has more asphaltenes here. but we were not able to analyze all samples because we got some unexpected results with the domain structure, with the asphaltene and domain structure. Anyways, in general, the conclusion here shows that both types of bitumen used in this study improve their mechanical and rheological properties upon the addition of a food-based additive. The microstructural studies with the atomic force microscopy, it shows that this is a very promising technique to identify the improvement in the characteristics of the bitumen binder improved with the additives. And the bitumen added with the food-based additive confers strength to the conglomerate and improves and increases the lifespan of the paved roads. Thank you very much for your attention.